Next we will find the normalized transfer function h of Sn of Butterworth low pass filter. For even n, we have h of Sn equal to product of 1 upon Sn square plus bk into Sn plus 1 for k equal to 1 to capital N by 2, where bk is equal to 2 times sine of 2k minus 1 pi upon 2n. Here n is order of the filter and we have found it as 2. Therefore k becomes n by 2 equal to 1. Therefore h of Sn is equal to one upon Sn square plus b1 into Sn plus 1, because k value is 1 here. When k is equal to 1, bk will be equal to b1, that is equal to 2 times sine of 2 into 1 minus 1 into pi upon 2 into 2, that is equal to 2 times sine of pi by 4, that is 2 times sine of 45 degree, that is equal to 1.4142. Therefore h of Sn becomes 1 upon Sn square plus 1.4142 Sn plus 1. Now we can obtain unnormalized transfer function by substituting for Sn equal to S by omega c. Obtaining normalized transfer function of Butterworth low pass filter, h of S equal to h of Sn at Sn equal to S by omega c, where omega c is cutoff frequency, which means Now we have to calculate cutoff frequency. That is omega c is equal to omega s upon 1 by as square minus 1 1 upon 2n. Omega s we have calculated as 39.2522. As is 0.1, so 1 upon 0.1 whole square minus 1 whole raised to 1 by 2 into 2, that is 4. Simplifying we get 12.4439 radians per second. Substituting omega c value, we get h of s equal to 1 upon s by 12.4439 whole square plus 1.4142 into s upon 12.4439 plus 1, that is equal to multiplying and dividing by omega c square, that is 12.4439 square, we get 12.4439 square divided by s square plus 1.4142 into 12.4439 plus 12.4439 whole square, which is equal to 154.8506 divided by s square plus multiplying 1.4142 with 12.4439, we get 17.5982. Here I should write yes plus 154.8506. Here constant term and numerator both will be equal. So this is h of s, that is unnormalized transfer function of Butterworth low pass analog filter. Now using h of s, now we have to convert h of s into h of z by using BLT. Obtaining h of z, h of z is equal to h of s at s equal to 2 by t into 1 minus z raised to minus 1 upon 1 plus z raised to minus 1. That is 154.8506 upon 2 by 0.1 into 1 minus z raised to minus 1 upon 1 plus z raised to minus 1 whole square plus 17.5982 into 2 upon 0.1 into the bracket 1 minus z raised to minus 1 upon 1 plus z raised to minus 1 plus 154.8506. Multiplying and dividing by 1 plus z raised to minus 1 whole square by 400 we get h of z equal to 1 by 400 into 1 plus z raised to minus 1 whole square into 154.8506 divided by 1 minus z raised to minus 1 square plus 17.5982 into 1 upon 20 into 1 minus z raised to minus 1 into 1 plus z raised to minus 1 plus 1 by 400 into 1 plus z raised to minus 1 whole square into 154.8506. Simplifying, we get h of z equal to 0.1708 plus 0.3415 z raised to minus 1 plus 0.1708 z raised to minus 2 whole divided by 1 minus 0.5407 z raised to minus 1 plus 2.22 0.2237 z raised to minus 2. So this is the transfer function of digital low pass filter for given specifications. Now we have to realize this h of z using direct form 1 and direct form 2. So write here realization of h of z. H of z equal to y of z upon x of z, that is equal to x of z into 0.1708 plus x of z into z raised to minus 1 into 0.3415 plus x of z into z raised to minus 2 into 0.1708 plus y of z into z raised to minus 1 into 0.5407 minus y of z into z raised to minus 2 into 0.2237. Right here direct form 1. Structure. X of z gain is 0.1708. Show here one summer or adder. X of z into z raised to minus 1 is there. So show one delay box here. X of z into z raised to minus 1 is multiplied by 0.3415. Next you have to write x of z into z raised to minus 2 into 0.1708. Show arrow marks to show the direction of signal flow. Let us show here y of z, that is output, y of z into z raised to minus 1 gain is 0.5407 we are having here minus y of z into z raised to minus 2 into 0.2237. So show one more z raised to minus 1 box here, that is delay box. Minus 0.2237. So this is direct form one structure for h of z that we have obtained. Next we have to draw direct form 2 structure. In that what we do, we take left part to the right side and right part to the left side, and we use delay boxes in common. Now this is direct form 2 structure for h of z. Frequency response h of e raised to j omega. we can obtain h of e raised to j omega by substituting for z equal to e raised to j omega in h of z, that is 0.1708 plus 0.3415 z raised to minus 1 plus 0.1708 z raised to minus 2 by 1 minus 0.5407 z raised to minus 1 plus 0.2237 z raised to minus 2 at z equal to e raised to j omega. At z equal to e raised to j omega. So when we substitute and simplify, we get it as 0.1708 plus 0.3415 cos omega plus 0.1708 cos 2 omega plus j of minus 0.3415 sin omega minus 0.1708 sin 2 omega whole divided by 1 minus 0.5407 cos omega plus 0.2237 cos 2 omega plus j of 0.5407 sin omega minus 0.2237 sin of 2 omega. Now if we substitute for omega value from 0 to pi in steps, we can get h of e raised to j omega as a ratio of complex numbers whose magnitude we can calculate. Such a calculation is here now. For omega value 0 to pi in steps of pi by 16, magnitude of h of e raised to j omega is calculated. I request all of you to calculate these values using your calculator in complex mode, and also I ask you to remember that while obtaining an expression for h of e raised to j omega, to substitute for e raised to minus j omega equal to cos of omega minus j sin of omega Now have a look at these values, and by computing these values using your calculator, compare your results. Now we have to plot h of e raised to j omega magnitude versus omega. When we plot, we get a graph like this. On x-axis we are having omega value varying from 0 to pi, and on y-axis we are having magnitude of h of e raised to j omega varying from 0 to 1. And this is the frequency response of Butterworth low pass digital filter. So I'll write here frequency response of second order digital Butterworth IIR low pass filter. At cutoff frequency omega c equal to 0.35 pi. Remember, this omega c is digital cutoff frequency. The magnitude is 0.707. The magnitude is here 0.707. So the frequency response is according to the specifications. Dear students, I will stop the class here and continue in next class with another problem of designing a digital low pass filter using IIT transformation method. Thank you.